Okay, good evening. It's Bugisa Joseph.
And Nachamba Demariam, Group SWML 53.
Presenting to you LendShield AI, a dual model ensemble structure for microfinance credit scoring under severe class imbalance and institutional domain shift. So we shall progress to the next slide. We indicate the content of presentation, what we shall be going through. From introduction, problem statement, all through references to acknowledgement. The background and the introduction, we have Uganda's microfinance sector, whereby has savings and credit cooperatives and microfinances over 2,000, and they manage over 3 trillion annually, but they operate outside formal credit bureaus. And then we have portfolio at risk, whereby these institutions, they deal in lending borrowers, but they run this portfolio at risk of 15 to 25%. What do you mean by portfolio at risk? These are just the principal amount that has been disbursed to the people, and they are supposed to have repaid it already, but haven't repaid it, and they are over 30 days. So that gives us our portfolio at risk. So this 1525 is against the 5% world's benchmark, and that's the bad one. And the indication is that every 100,000, 25,000 may never be repaid, in simple. So we have the credit bureau's gap. So most of these institutions do not have the access to credit bureau for to to help them check, whereby to help them check if a borrower has defaulted in other institutions and wanted to borrow from them. They don't have the capability because they are unable to check. So appraisal bias, this is where loan decisions are based on relationships. So we have scenarios where our loan officers, most cases, based on the relationships, the feelings they have to grant loans to the borrowers, not basing on data or use of the affordability of the borrowers. So that's where our problems come from. And some key terms we have model one, that's our model for the gatekeeper model, which whose MVVP is already there. It is like for the pre-disbursement, and then module 2 for the monitoring already running loan, and it produces if a loan is stable, elevated, critical. And then XGBoost is our model that we selected, built and deployed, and then Sharp, we used it to generate explanations. Yeah, for AI explainability, reasons for the decision that has been taken. So related works. So we looked at also other works similar to what we have undertaken, and we can look at AI in banking regression analysis for credit risk. This work was done using logistic regression and linear regression models. It has architectural limitation and context limitation, does not capture the nonlinear relationship between the features, and then context limitations. So this requires formal credit history, and it's not applicable to Uganda. Why? Because most of our loans are managed informally. Data keeping is very informal. So, and then there are other works also, and we compared them with ours, which also have other limitations. It's a limitation like we are still only in a single country, federated, running, not yet implemented, like looking at other countries. Yeah, so that's the comparison. Of course, shall progress. So, problem statements. So, what's the problem actually that brought us to this research? So, with the main application problem, we have the appraisal bias, as we said lastly. Most of the loans just approve it because of the feelings and the friendship, relationship, not actually on data. And then identity and trust gap. No universal credit score for tier 4. So defaulters can borrow here and then run the other side, and then they also go and borrow again. They default, they run somewhere else. So blind spot, so running loans, like there are no indications, clear early indications, like a loan is now heading towards being defaulted. The borrower starts misbehaving, so showing red signs, but there are no systems that help alarm for these loan officers that this loan is heading in bad direction, carry out some action. Those systems are not there. They only realize after some time when the loan has been defaulted, the person ran away with the security. Yeah, those are the issues. So computation problem, we have currency balance, whereby the data is real world data collected from over 60 cycles, 20,000 records. So this data is going to have or has majority of the loans fully repaid well, and a few which were defaulted. So that gives us a class imbalance of in the target feature, and the feature that like what we are trying to predict. Majority are the yes, and then the no's are very few. So a model that is naively trained can have 83% accuracy, while detecting zero defaults at all. And then, so that has to be taken serious. The institutional leakage, so data from different a given institution carry certain pattern. So when this data is split into train and test data from one institution, going in both ends. So you'll find that the model will have high accuracy. Why? Because just uses the pattern that it learns due to the data from an institution being in a train, and then use the same data for testing. So it will learn. So now there we have a challenge of carrying out independent split. Like we make sure when we split, full data goes to a full data about a given circle. If it is in training, it has to go only in training. If it is testing, only testing. So when we look at research questions and the objectives that we have, so um, we have about 4 research objectives and then also 4 questions. So one of the objectives was to conduct 24 question exploratory data analysis on the 20,000 records. Also, to design, train, and compare our models so that to come out with the best module, to also deploy an API how they can access our module and use it for the good, and then also to establish the deployment phase, 3 deployment phase, which is the shadow assisted policy, which shall look at the next slides. And then our questions, the questions that we have, such questions that we try to answer during our research. What borrower, loan structure, and contextual features carry the highest predictive signal for loan default? So what are those features that are going to be carrying the most signals or weight for prediction? What are those features that will help in predicting the behavior of a given loan, or whether a loan will default or not? And then which module helps us achieve the goals that we have of application gatekeeper and the learning loan monitor? And then what early repayment project, what are those features that indicate for us that the loan is moving in the right direction? What are those features that are going to help us flag loans as stable, elevated, or critical? Then how can we use CHAP-based explanations to structure and provide actionable regulation compliant adverse actions? Um, and then this our contributions, research contributions. So we conducted the 24 ED framework for Ugandan Circle. So EDA framework for Ugandan Circle. So we carried out 24 data analysis where we made key findings and insights, like we looked found overcollateralization paradox instances of like if collateral is marked as excellent, they are the ones which have the highest default rates, school fees, seasonality effects in Uganda, January, and many others. So we also performed about the EDA. We have a full video on YouTube explaining the EDA phase. We performed a 5-model comparative evaluation. Also this, we also have full video looking at model training evaluation, leakage auditing, and all those. And then we also deploy the production ready services. So we build the APIs, put it in production. It's already ready for testing, fully functional using Flask REST API. We also established trusted MVP, so minimum viable product with three-phased deployment framework. And then methodology and system architecture. So we use a block diagram to indicate the process that we went through. So we had data ingestion, which involved the data extraction. We had to write a data extraction pipeline, which were scripts that we used to extract the data, the 20,000 from over 60 circles coming from different databases. And then exploratory data analysis phase is where now we carried out quality audit, feature discovery, and then leakage patterns identifying. So we had to discover a lot of insights, make insights, and then make decisions, modeling decisions, which we carried on to feature engineering. So, so from feature engineering, so we implemented those decisions that we made from exploratory data analysis. And then model training, where we trained our models, evaluated them, tested them, and then we look at a leakage auditing, whereby we had to carry out series of steps, 7 steps, to check permutation, importance check, to make sure that our models are, the model are being trained on data that is leakage free, accurate. So then we deployed. And then model architecture and the mathematical foundations. So so we look at the mathematical foundations. So we are going to focus mainly on XGBoost, the model that we selected. We discuss its mathematical foundation in slide detail. Then the others, we have full videos discussing those ones there. They are there on the YouTube. So we have the objective function made up of loss functions, which takes in the actual value and the predicted value. If the model is wrong, this value goes high. And then we have regularization function whereby this one is going to help us control the model from building very complex trees where it just remembers the data but suffers in the real world. So this is the penalty on any extra tree that is made. Only make sure the module trains the model grades tree when it's actually necessary. So this function here is indicating for us the additive learning, whereby this one is the actual prediction, then these are predictions from other previous trees. This is the learning rate, whereby we only from the prediction that the current model has made, we only take, for example, 5%, given we have 0.05 learning rate. So these are the models due to time factor. We are going to refer to the videos that we discuss fully, model evaluation training.
And then here I'm going to look at the dataset description and the explanatory data analysis. As we look at the dataset, we have the source is having 20,856 loan records. And these are from 60 plus Ugandan circles across 15 districts. The variables are in 73 columns, and those are in 7 groups. You can see that the variables include the identifiers, loan status, borrower demographics, loan terms, application, and collateral. We looked at the target. The target was that if the default flags 1, it means it is defaulted, and the class ratio shows that 16.773% is the default rate, whereas the balance is the non-default rate. So the imbalance is a ratio of 4.3 to 1. The privacy shows that all the PIs, the mobile number, the NIN numbers, those are of course the IDs, then the registration. These ones all will
hashed
hash to the complaint with Uganda DPA, and this was in 2019. And the quality issues, we majorly looked at that 88 columns were fully null, and this leads us to 80 to 100% accounting inconsistency in top 20 SACCOs. The EDA results are in the next slides. As you can see, of course, we didn't bring out everything. Most of them are in the EDA slides that we shared earlier on in the previous submission. So today we're going to majorly look at the class imbalances. One of the constraints you're looking at is the class imbalance, and as you can see from this graph, you can see that there is a class imbalance from the fully paid and those that are written off. So if the number of loans that are fully paid are higher than the ones that are written off are low, you can see that there is a huge class imbalance. And then when you look at the over-collateralization paradox, here you can look at, I'll explain this in real world, like the people that acquire loans but have no collateral, they tend to default highly, and the default rate is 16.8%. But those that have put collateral here in the green graph, they have 15.2%, and that is lower than the ones that have put collateral. And there is also an imbalance, as you can see. When we continue to the to the duration default monotic relationship, you can see here that the duration of the loan, when the duration of the loan is less than 30 days, the default rate is less. But when the default rate is above 366, that's a year and above, it means people can highly default, and that's 51.6%. In the repayment cycle, this is the variation in the repayment cycle and the business type. I'll use one business type. For example, when you look at the border here, the default rate is rising, is zero, and their repayment cycle is a bit.
For daily repayment.
But the one for daily repayment is lower. But when you look at the ones for other business types, we can see that there is a change. According to the bigger I'll use this, the bigger the business, the bigger the repayment cycle increases. When you go to the borrower loyalty effect, here the borrower, we look at the people that have acquired loans for the first time, the second time, and those that have been constant in accessing loans. Those that are first loaners, there is take up high rates defaulting, and those that are always, the ones that are known, there is having a lower default rate, yes. But now, when we look at the variation of the school fees seasonal effect, here we look at the months of the year. You can see that in January, the default rate will be high because you know how students are going back to school and they have to pay tuition. So parents will acquire loans and the default rate will be high. When we reach May, the default rate is low because students are in holidays. And then when we go to September, the default rate is again low because they are in holidays. But in July, they are at school. They have acquired loans and default rate is high. But then in December, it is low because the students are home. And then the output results and discussions. Here, we looked at the models. We got averages of which model performed the best, and the XGBoost actually gave us the best results because it showed us that the model was accurate by 0.766, which makes it the best because of its stability across 6 circle group splits, reshuffles. When we go to the explainable AI,
okay, so explainable AI results and the discussions. So so we look at the 7-step leakage audit that we carried out, and as I said, we carried out to permutation importance, whereby we had to identify, like, according to how the features are contributing in the prediction. So is there any feature that is like that we are that is suspicious of leakage, that we are suspecting is a post disbursement feature? And so we found out that all applicants were okay. Then we also did the same for RF feature importance, and this was fine. And then we looked at also duplicate detection. So, like, here we are saying train test intersection. Are there any data that are existing in a train or test? Because if you data is there in a train and then you put it there in test, so the model will just predict it accurately without any problem. So we had to verify that all those nothing happened. So, and then this one here, basically what is showing us which feature, engineered and non-engineered, have the non-engineered, like their contributions to the predictions. That's basically what our sharp group importance is showing. And then we have model selection and deployment. We basically selected the XGBoost module. We said, what did we do? We had it to run across 6 group split, and in every split we carried out training, validation, testing, and then we summed up the average of the results, and then we got standard deviation compared among all the 5 modules, and XGBoost became the winner, and that's how we selected XGBoost. And then, of course, deployed that module, and then we exposed the API endpoints for usage, and then we defined the series phase, whereby we shall now take this module up to production grade and the consistency with the UMR approval. So the phase 1 is the shadow mode, which we are in right now, whereby it runs parallel with manual process. So predictions are logged, no decisions altered yet. So it is there, but predictions are logged. So, and then to demonstrate what our model is doing, so render will really take time to open. We'll be going and paste it, but because they always shut down the server if we are inactive, but we have screenshots here. For due to time factors, we are going to demonstrate. So with the interfaces here, whereby we submit in mail 34 yards and other variables, no collateral. No collateral, of course, gave us a high risk. And yeah, that's our module in action. So we look at then the limitations due to time, which I'll just be wrapping up. So we have data quality issues, columns are null, we have placeholders, accounting inconsistencies. And those are the limitations we have. Then we also have problems with our deep tabular models, which are data hungry. We have few datas. Yeah, and then XGBoost architecture also, the temporal dynamics issues and attention based. What is the problem here? It doesn't have memory, doesn't capture change in behaviors. Yeah, those are kind of the limitations that we have. We are just wrapping up now. In conclusion, we say this is one of the first modules that is leakage audited for credit frameworks in Uganda. And then our 24 EDA revealed a lot, the collateralization paradox and school fees seasonalities. Yeah, and then our future works, we are looking at recollecting data again to gain massive data and then more clean data. Yeah, without those limitations. So actually what we are looking forward to. And then also maybe USSD interfaces, form edits. Yeah. And then references. These are the references that we have. And then we have acknowledgements. We acknowledge so to our supervisors.
And we come to the end of our presentation.
Okay, thank you for listening.